In this video, we are going to be learning about arithmetic sequences and summation notation. Okay, so let's get started. First, we need to understand what an arithmetic sequence is and what summation notation is. First, let's start with what an arithmetic sequence is. An arithmetic sequence is an ordered list of numbers where the difference between each consecutive term is always constant. So let's get some examples of arithmetic sequences. So an arithmetic sequence could be 1, 2, 3, 4, 5. It could also be 2, 4, 6, 8, 10. It could also be hang on. Let's pick some random number. 1, 9, 6, 4, 5, 2, 3, 9, 2, 9, 0, 4, 5, 8, 9, 3, 5, 6, 7, 3, 6, 9, 5, and the fifth term is getting too large. Okay, so those are some examples of arithmetic sequence. So there's also a formula for an arithmetic sequence, right? The formula is, if I had some space, let's just do right here, right? The formula is A of n equals A1 plus n minus 1 times d. So here is what each value represents. A1. Here, let's actually get this sequence right here. So A1, we have A1 being the first term. Right? So for this sequence, that would be 2. Now for n. So this is n1. Yeah, so this is n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. So this is just what number, basically where in the sequence the number is. So for our case, the number 2 is the second number in the sequence, hence it is n2. So n is just the position of the term. And finally for d, d is the common difference. right? So let's test that out on a series, right? I actually don't know if this series is correct for each term, so it's nice that we can just check this, right? Oh, and so the common difference of this would be 2 and the position of the terms. Okay, so let's try and use that as an example for another sequence. Right, so I need to erase this. Okay, let's say we need to find the fifth term, right? So a and then the term is 5. So then the term number 1 is 1,900, 196,452 plus we want to find the fifth term, so 5 minus 1 times the common difference. So the common difference is 392,904 minus 196,452. So the common difference is 196,452. So now if we compute all of this, hang on 1 second. We'd get A of the fifth term would be 982,260. Yeah, so that is a basic introduction of arithmetic sequences. So let's get started with our questions. Oh, and for summation notation, we're going to be doing that in the next video. So questions 1 through 5. Write the first 4 terms of each sequence. Okay, well that's pretty easy. Just plug in 1, 2, 3, and 4 for each number. So 5 times, I'm just gonna duplicate this a bunch of times. So 1, 9, not 9, 2, 3, 4. If we plug all of these values in, we'd have 4, 9, 14, 19. And this is our answer. Time for this one. So 2, 1 and 1, 2 and 2, 3 and 3, 4 and 4. And if we solve, we get 3 over 4, 1, 7 over 6, 9 over 7. And that is our answer for the second question. This is negative 1 to the power of hang on, just give me 1 second. Okay, so this is negative 1 to the power of the n, and I promise this is in tetration. Tetration is another very not theoretical, but it's just a whole entire type of exponentiation. But yeah, that's just not used that much in pre-calc. So n minus 1 squared. Right? Duplicate. Now you put in the values. Okay, now we plug in the values. So 0, 1, negative 4, 9. Oh yeah, you can't do that. That is our answer to the third question. Use the following n values. And since you guys probably get the gist of it, the answer for this is 0, 3 over 5, 4 over 5, 5 over 17. And you can pause the video here if you want to know what the answer is. Okay, so the answer is 1, negative 2, 3, and negative 4. Okay, on to question 6. So question 6 asks something different, right? It says, what values does a of n equal such that you get these values? So what values of n could I plug in to get these values, right? So you could very easily just solve, right? log base 3 of n equals 1. So what would that be? N would obviously equal 0 because any value of any log that equals 1 is automatically 0, right? So what base log of 3 is equal to 1? And the log base 3 of 9 is 2. And log base 3 of 81 is 4. So our answers are 0, 1, 2, and 4. I think I have log videos in my channel. You can take a look at those. In question 7 and 8, this is finite. And this is infinite. Because in a series, if they list it out and there's dots at the end, that means it goes on forever. And let's just do question 16. These questions are for summation notation, but this one isn't. Ooh, so this answer is actually really, really interesting. Yeah. Okay. So we already know that, so I'll just write the sequence here. A1 is equal to 1. And A2 is equal to 1. Right? So now we just have to find the value of 3. So let's plug it in. A of 3 equals A of 3 minus 1 plus A of 2 minus 1. A of 3 equals A of 2 plus A of 1. A of 3 equals 1 plus 1. A of 3 equals 2. A of 3 equals 2. And now for 4, so A of 4 equals 4 minus 1, and yeah, these should be 2. 4 minus 2, so A of 3 plus A of 2 equals 2 plus 1. So A of 5 equals 3. And for phi, this is really simple. Obviously, it's just going to be 3 plus 2. So 5 is going to just be 5. So it's 1, 1, 2, 3, 5. Okay, and yeah, that's it. That's the end of this video, but if you want to stick around, if you know what the Fibonacci sequence is, then you would know that this is the Fibonacci sequence. Basically, the Fibonacci sequence is each term just adds on progressively. So 1 plus 1 equals 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13. So it goes on like that. But there's something really interesting about the Fibonacci sequence that I kind of want to share. So we have I had to make this color coded. Right. So that is a 1 by 1 unit. So what's the second term? That is another 1 by 1 unit. Right? So now we need to do a 2 by 2 unit. Right? We have that. So now we need 2 plus 1 is 3. So now we need a 3 by 3 unit. Okay, so it's not lining up perfectly, but yeah, we can just say this is a 3 by 3. Right, and then now 3 plus 2 is 5. Right, so we started with the Fibonacci sequence. So the sequence is 1, and then it's 1, and then it's 2, and then it's 3, and then it's 5. So let's keep on going. So now we need 8. Okay, now we have 8. So let's keep on going. So we have 8. Do we have space for 13? Probably. Yeah, we do not. Okay, let's move this down. We barely have space. We just have to make do with what we can. So this is probably going to be the final block. Okay, so now the moment you've all been waiting for. why does this matter, right? Well, we can draw this. You see, it's a spiral. Can we get a 13 plus 8? I don't think we can. That'd be 21. Let's try. Oh, so we can. Yeah, and that is the Fibonacci sequence. Can we actually get one more? So let's write this down. 13, 21, and now it's 21 plus 13. So a 34 blocks, holy. A lighter color. Yo, so we got an extra 2 boxes. That is a Fibonacci spiral, right? So we start at 1, 1, 2, 3, 5, 8, 13, 21, and then 34. Isn't that cool? So now the next time you look at the Milky Way, you know that the spiral actually comes from a Fibonacci arithmetic sequence. That's really cool, right? Anyways, thank you for watching this video. We're going to be going over summation notation in the next video. Thank you for watching, and bye.